So today's lectures on moments inequality. These are very important for calculation of some bounds on probability. So the first theorem is this is standard basic theorem. Let Hx be a non-negative Borel measurable function of an random variable x, then expectation of and assume that expectation of Hs exists. Then for all epsilon positive, what happens? The probability of Hx, which is greater than or equal to epsilon, is less than or equal to the moment that past moment, that expectation divided by this. Sometimes it's called Markov or Chebyshev, whatever. This is the basic thing, and some sort of variations are there. Sorry, again there is a problem. It's the last page. So again, so moments inequality is lecture 8. The theorem, the basic theorem is this. So let Hx be a Borel measurable function of random variable x, and assume that expectation of Hx exists, that is finite. Then for all epsilon positive, that probability of Hx greater than or equal to epsilon, which is bounded by this quantity expectation of Hx by epsilon. So proof is very easy. So we prove it for discrete. So assume that x is discrete, and similarly you can prove it for continuous case. X is discrete. Now let probability of xn equal to xk, that value is pk. So with that k equal to 1 up to dot 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 dot, maybe finite, maybe infinite. Now then what happened? Then expectation of Hx sum over k, that k may be a finite sum or maybe a series sum, and since it is non-negative, so it is Borel non-negative Borel. So Borel non-negative, so this is positive and this peak is also positive, so you can rearrange the term, whatever, you can set any rearrangement there. And that summation is over two sum over all over the A, some k's, and some over the A complement. What is A? So we break this sum into two parts, one for A and another for A complement. And what is the A set? The A set of all such k such that hk is greater than or equal to epsilon. So we break two parts, one is greater than epsilon and another is less than epsilon. Greater than or equal to, another is strictly less than epsilon. Now what happened? Then we can say this is just greater than the one since so this is summation A hk pk. Just we expectation is a sum of 2, so we just drop 1, so that must be greater than equal to is equal to this part, and this a in a the hk is greater than equal to epsilon, so every value is greater than equal to epsilon. That means it is greater than or equal to epsilon into sum over pk over that a. Now this sum is actually the probability, so this is the probability of hk greater than equal to epsilon. So done. So we have this proof. Now the some corollaries are there. Sometimes it's called the Markov inequality. We just let hx equal to x to the power r, mod of x to the power, so non-negative, and epsilon say k to the power r. Some r is some positive, and k is also positive. Then if you use this, then what happens? Expectation of hk is just mod of x whole to the power r, and that is okay. We write the probability first. So probability of mod of x to the power greater than k to the power greater than or equal to k to the power r, which is less than or equal to expectation of hk, which is expectation of mod of x equal to the power r divided by k to the power r. Now this is, since mod x is positive and k is positive, this is equivalent to say that the probability of mod x, which is greater than equal to k, is less than or equal to expectation of mod x equal to the power r divided by k to the power r. So this is called something called Markov inequality. Now, in particular, if we take hx equal to k, if we take hx equal to that x minus mu whole square, the mu is actually the expectation of x, which is the expectation of hx is the variance. So expectation of hx is the variance of x. Now in that case, what happens? In that case, then probability of hk is that x minus, this is non-negative, greater than equal to, we take epsilon equal to say k square sigma square, positive. So k is positive, some k positive. Epsilon is this is variance x. So this greater than equal to k. This is greater than equal to k square epsilon square. This is the k square sigma square is less than or equal to expectation of x, which is variance, divided by k square, divided by that epsilon. Epsilon is k square sigma square, so k square sigma square. Now this implies what? This is just expectation probability of mod x minus mu, which is greater than this mod value positive, so greater than equal to k sigma, which is less than or equal to the variance of x is sigma square, so 1 by k square. So this is the very important thing, and if you just take the standardized thing, so it is actually written in the standardized form. So it is in the standardized form, then the every standardized random variable, which is the probability which is greater than equal to k, is actually less than or equal to 1 by k square. And you can break this to in minus k to k. You can just write in. So you just this is and you can just write the equivalent form, that mu minus k sigma to mu plus k sigma. That probability is less than or equal to 1 by k square. So it is bounded by something. So this is very important thing, and you can just use and in for various distribution like no. So this is true for continuous case also. Continuous case you have to just take the integration, improper integration of integration. For continuous case you have to the expectation of hx for x continuous, and actually not only the x continuous, hx is also continuous. So there is a problem if hx is continuous, x is continuous, hx is discrete. So this, in that case, you have to take the integration over minus infinity to infinity hx fx the PDF dx, and you have to take two integration, two part. One is one integration over that similar a and a complement, and that a part is actually the set of a. The set A is actually a set of all x, such that where this hx is greater than or equal to epsilon. Same thing. Now this is a, since h is Borel measurable, this is a Borel set. That's the important thing. So similarly, you can prove it for continuous. So this is very important thing. And one lemma for that in this inequality is one lemma. This is important for the next in convergence part, CLT or weak Laplace number, strong Laplace number. So this lemma is let x be a random variable. So with expectation of x is 0, say. It may be symmetric about 0, so it is expectation of x 0, and variance is sigma square. Like normal, standard normal or normal with mean 0. Then probability of x greater than x is just less than or equal to not only that 1 by that part, that is actually sigma square by sigma square plus x square. So this is very important. So it is sigma square if x is positive, if x is positive, and the probability of x greater than or equal to x. Now x may be now in Markov or that theorem, Markov inequality, that x is non-negative, that the standard basic theorem. By the way, that is called Chebyshev inequality. That the previous one is called Chebyshev inequality. This is called the Chebyshev. This part for this is called the Chebyshev inequality, which is called Chebyshev inequality. Now that is for non-negative, but here x can be negative, positive, everything, negative variable or mix negative positive. X contains negative positive everything. In that case, for if x is negative, then it is greater than or equal to sigma square. Sorry, x square by sigma square plus x square. That is interesting. So if x is negative, and if x is 0, then it is half. It is half, just equal to half. So what is the proof? Proof is like that. So you have to choose a proper function, t plus c whole square, that for t positive. Then ht is actually positive, greater than or equal to 0 for all t, and also ht is greater than or equal to x plus c whole square for all t x, for all x, such that x is in between 0 and t. Okay, just write for all x and for all t also. Now, if you use that standard basic theorem, what happens? Then x greater than or equal to x is positive, is equal to probability of that hx is greater than or equal to x plus c whole square, less than or equal to, because it is a if x greater than x, then this is a superset. The right hand side part is superset, and this is again by that result, that basic inequality is this expectation of this divided by x plus c whole square for all c positive and for all x positive. Now, what is the expectation of x square? X plus c whole square. The expectation of x is 0, so expectation of x is 0, and expectation of x square is sigma square, and expectation of x is 0. So variance is the expectation of x square is actually same as variance. Now Now we know this is so when this is minimum, when this so for all c this is a function of c. The right hand side is a function of c, and we already proved that this probability of x greater than x, that is less than or equal to something which involves some c. But what is the minimum value of that c? What is the minimum value of c? So that right hand side, this is minimum. This is minimum. You can check that this is minimum when sigma c equal to sigma square by x. Then it is minimum. So when c equal to sigma square by x, then it is minimum. Now what is the expectation of x plus c whole square? So this is expectation of x square, which is sigma square, then 2 into c into expectation of x, which is 0. So expectation part of the 0, product term is 0, and then c square. So actually, so what happened? So the probability of x greater than or equal to x, which is less than or equal to sigma square plus c square by x plus c whole square. Now question is, when it is minimum, that this is minimum. So you just replace this by sigma square plus c square. So this is minimum when c equal to sigma square by x. That you can check easily. And so if it is minimum, and right hand side is function of c, and the left hand side has no c, so since it is true for all c, so this should be true for the minimum value of the c. So that means that is this is less than or equal to sigma square by x. That is c, sigma square by x. That whole square divided by x is just x plus c is sigma square by x whole square. So what is sigma square plus sigma to the power 4 by x square divided by what? X square plus sigma square whole square divided by x square. You just multiply by x square, then x square sigma square plus sigma to the power 4. Is it coming? X square. Yes, it's coming. So you take the sigma square common, and one x square sigma square cancel out, so x square plus sigma square. That's, and you just check this is minimum for this value. You can just take the derivative or whatever. You just find just algebraically, or you can easily find by derivative, and take derivative 0 and then find minimum, the second derivative positive. And similarly, you can check for this similar proof for x negative. So this is left as an exercise. For the negative case, left as an exercise. So these are very important some results. Now I give two theorem without the proof. Proof is omitted. You can just try yourself in after class. That one theorem is let the fourth moment is finite. Assume that the fourth moment is finite, and expectation of x is 0, and expectation of x square is actually sigma square, which is variance. Then its probability of mod x greater than or equal to k sigma is actually less than or equal to mu 4. Mu 4 is the fourth center moment minus sigma to the power 4. Oh no, mu 4 is the fourth raw moment. That by minus sigma to the power 4 divided by mu 4 plus sigma to the power 4 k to the power 4 minus 2 k square sigma square for some k greater than 1. So this is one theorem. You just you have to substitute you replace that x, replace x in the previous theorem, replace x by that x square. This is the outline of the proof. X square minus sigma square by k square sigma square minus sigma square, and take small x as 1, which is positive. And you just in the previous theorem, you just replace this and you will get the values, these calculations. After calculation, you will get this bound. The next theorem is also very important for the limit theorem. This is called Lyapunov inequality. So let beta n are the nth order raw moment, which is finite, and this is for any arbitrary k is between 2 to n, say. Then this is very important. Result is that beta k minus 1 whole to the power 1 by k minus 1. So right, whole to the power 1 by k minus 1. This is actually less than or equal to beta k whole to the power 1 by k. So this is interesting. So proof is omitted. Proof omit. You can you need some quadratic forms that proof omit. So these are very important inequalities, and we have some. We give some examples. Say the one important example is like that. Say you take say x is x as a PDF. X as PDF. Fx equal to 1. So it is uniform rectangular distribution, and 0 otherwise. This is 0 otherwise. In this case, what is expectation of x? This is actually half. We know this is half. And expectation of x square, which is the variance, is also half, and the variance is you calculate that variance of x is that 1 by 12. You can calculate. If it is from a to b, then it is b square minus a square by 12. Rectangular. Then probability of x mod of x minus half, this less than or equal to, we take that epsilon as a 2 into 1 minus root 12. That is root variance is 1 by, the sigma is root over 1 by 12. You take the sigma as 2. Then it is the probability of half minus 1 by root 3 to x to half plus 1 by root 3, which is actually equal to 1. We give this actually equal to 1 because this is negative number and this is greater than 1. Yes, it is greater than 1. This is negative. What? It is half plus 1 by root 3. Yes, root 3 is less than 2. So 1 by root 3 is greater than half. So the right hand side is greater than 1 and the left hand side is negative. So it is 1. The probability is 1. But if you use the Chebyshev inequality, if you Chebyshev's inequality, if you use that, what happens? In that case, it say the probability of x minus this greater than equal less than equal to 2 into root over 1 minus 12, 2 into root over 1 by 12 is greater than equal to 1 by 1 minus 1 by 4, which is 3 by 4. So this Chebyshev inequality says this probability is greater than equal to 3 by 4, but actually this probability is 1. That means the Chebyshev inequality is not a good bound. That's why you improve the next theorems. And there is a one better bound is called Charnov bound. That is not in the syllabus, so I omit this. The Charnov bound is actually is better than that Chebyshev and Markov. It's actually more good bound, give good bound, the Charnov bound. So that's all for this lecture.